Hello, everybody. This is Barry Stevens. I'm from Ventacity Systems, and I'm going to be sharing this presentation today. Really excited about that, and welcome you to the Passive House 2020 conference.
Well, and here is Berthold Kaufmann from Darmstadt, Germany. I'm with the Passive House Institute since some years, and I'm as well very excited to do my first recording here, my first online activity.
And what we're going to be talking about today is outside air, better known as ventilation. And so we are going to really talk about ventilation done the Passive House way and the importance of efficiency and other very important aspects, especially in today's world. As we do this recording, we're in the middle of a pandemic, and that really plays up ventilation in a big way. So with that, we're going to get started.
Okay, here a short summary to make it a little more general for passive. So it's ventilation for passive house buildings. And basically, to talk about indoor air quality and air comfort. This is what the client of passive and living afterwards in a passive house are feeling. And we are working to get this quality good. And therefore, we have to take some things ready. And therefore, we will call about ventilation system with heat recovery, with humidity recovery, well, and in general, how to assure good quality and so on. You can see some hint about the motivation with regard to energy. If you look at this graph, you have a monthly energy balance of a typical passive house building. And this is the yellow and the gray bars for January up to May, June, July, and so on. And you see the yellow and gray is about passive house, and the gray is for heating for passive house. But the violet things, this is if you go for a so-called low energy building without a ventilation system, without heat recovery. And you see here in winter time, the heat recovery helps us to have lower heating energy and to get the comfort quite higher. So no cold air coming in to the building. Well, and in summer, we have about the same vice versa, but this is not on the graph. Talking about air quality, air quantity, to make sure that that's enough air change and not too much. Yeah, please be careful. So, well, on the next graph, you see comfortable indoor air humidity. The point is, you see the green area here. This is the comfortable range in an indoor environment. And you see in winter, we want not to have less than about 20 degrees centigrade on the right axis. And in summer, we want not to have more than about 25, 26 degrees centigrade. And with humidity, relative humidity on the left axis, you see in winter, please not below 40%, and in summer, not much above 65 or 70%. Well, and to keep in this range, there are some hints to do, and it's quite easy to do it for passive house buildings. There are some quantities by numbers for to get typical air quality in buildings, inside buildings. And you see the international standard denotes 4 quality levels. It's either indoor air quality 1, 2, 3, and 4. IDA stands for indoor air quality. And you see the high and medium. This is for technical issues. So if you have a lab or a medical room or what else, this might be quite good for that, but it's not suitable for residential and for office use. So we recommend to go down for IDA 3, or if you go for meeting rooms, for schools and so on, you might even go lower for IDA 4. And that means the recommendation is only do please 30 cubic meter per hour in person for residential buildings, and maybe 20 cubic meter per hour in person for non-residential buildings, so for classrooms or meeting rooms where many people are in. If you would have more than this, please you must be aware that there will be too dry air in wintertime. Yeah, if you have too much airflow coming in, this will dry out people and they will complain afterwards. Well, and for this, now Barry will explain a little bit more in detail why ventilation and how to go for it.
Yeah, better ventilation means better health. And this is something that's really been rising, especially here in North America. We've seen, these are some studies on the screen that have been done. California did a study, and they determined that illness absences increased or decreased by 3.4% by increasing from 8.5 CFM per person to 15 CFM per person. For California schools, that translates into not only better health for the students in the school, but by not having as much absenteeism, they actually get more money from the state. So it actually is a both financial and health incentive for schools. And these studies have been done continuously, and we're seeing more and more data, more and more studies that are in a big way really demonstrating that ventilation is key to a lot of things in schools. It also means better performance. There's a study at the Harvard School of Public Health, did at Syracuse Center of Excellence. It was a double-blind study based on CO2 levels, and which really was representing ventilation rates. And what they found was on a green day, which is reducing CO2 levels from approximately 1,200 parts per million to 800 to 900 parts per million, cognitive function in a double-blind study increased by 61%. The green plus day, which is represented by 600 to 700 parts per million, is 101% better cognitive function. And the most affected categories of cognitive function were crisis response, information usage, and strategy. Just by chance, usually the conference room is where all those things take place. There's a crisis, everybody runs to the conference room. Conference rooms famously don't have great ventilation when they get full of people. And so this is a really critical thing to determine that performance is better and ventilation is a critical element of that. In the age of COVID-19 and a pandemic, there are a lot of people that are starting to talk about better ventilation on infections. And this study, which was done actually back in the early 2000s, was looking at classrooms and the spread of virus, basically. In this case, it was about the flu, but the COVID-19 would be very much the same. And what this found was that based on CO2 levels, so they were tracking CO2 levels as a determinant of the amount of ventilation. And what you see on the screen here are three arrows. I'll use my drag on this. This is for 1 hour, this is for 4 hours, and this is for 8 hours, the yellow track. And what they found was, if you look over here, this is the incidence of spreading of a virus in a classroom full of kids. And this is the percentage here. And as you can see, the percentage went up dramatically with the CO2 levels on the horizontal graph at the bottom. So the higher CO2 levels representing less ventilation determined that virus is going to spread to more kids in the classroom. A lot of this is common sense, but there is data, and we're finding that better ventilation is critical to reducing the spread of pathogens, whether it be viruses and other, just regular common colds, flu, and in this case, recently COVID-19.
Well, and with this, we are back about ventilation. And what Barry says is you have to have in mind ventilation means outside air in and used air out. So no recirculation air flow. Yeah. And this is the most important problem with this disease and the COVID-19 spread and flu spread in a building. If you would do a recirculation ventilation, this will spread out the problem all over a building. So, and the other point right now, back to air humidity, is we have to find a balance not too much air in, air out, and not too low. Yeah, and this is shown again here on this graph. Please check not to dry out your people and your building.
To demonstrate this, what you have is on the left is an HRV, and we're looking at this box is the comfort box for the relative humidity inside the space. And this is an HRV, and this is an ERV with the very same conditions. And what this really demonstrates is that you have the red dots here are supply air, temperature, humidity. The yellow is exhaust air. The brown is exhaust outside, and this is the outside air in green. So what you're seeing is the red dots, the supply air temperature is very close to this 20 C or 68 degrees Fahrenheit. So this sensible effectiveness is very high with the HRV, but these red dots are getting a little bit outside of our humidity here. With the ERV, you'll see that those red dots indicating the incoming air, there's a little bit of a trade-off between an HRV and an ERV. The ERV has a little bit lower sensible, so those incoming air temperature is a degree or two lower. But what you see is the relative humidity of that air is in the box. And so we're retaining humidity in the wintertime. We have a small penalty for sensible or the incoming air temperature, but that's something you look at. And people ask us, should I use an HRV and an ERV? And you have to look at this and determine what your optimum is going to be, where you are, and for what type of building it is.
Yeah. Well, and we will come in some more detail later to an ERV and HRV. So what's about humidity recovery? So we will explain a little bit more. Okay. The next topic is about CO2 level. Barry already mentioned it should not be too high. And the point is how to get it low. And it's quite simple. Run your ventilation system, so you will get will be able to keep it below 1,000 or keep it in reasonable range. And here we showed just this is out of a meeting room in Darmstadt, and it shows a so-called hybrid ventilation during 5 days. As the ventilation system is a little bit too small, it will only be able to keep the air good for about 2 hours with its 15 people. And in breaks, you may open windows if people stand up and so on. So it's no problem. Well, but in meantime, the CO2 level with the ventilation system can be kept quite below this 1,500. So about 1,200 or something, it's quite good. Well, and with that, we come to the question, what is about the air change rate in national standards, how to deal with passive house on the next slide. And the point is, many national standards ask for more and higher ventilation rate than we recommend. Yeah, you remember we recommend about 30 cubic meters per hour, and the German standard and Austrian standard and many others, and I think the US as well, they require for much more airflow. And so the point is you must have a compromise. So the idea is if your national standard asks for a higher airflow, you have to sign your ventilation system to cover the maximum airflow setting. But you can recommend to the user later to have the system running with a lower airflow. This is a compromise which can work, but you have to decide and to discuss it with the client anyway. Well, but on the next slide you can see again some numbers, and this is step one. You go for the standard and look what you need. And for passive house recommendation, you again have this 30 cubic meters per hour. But then you see on step two, what about the typical settings? And you see the nominal flow rate, 100%, is a little bit too high. This should be done only if it's really necessary. Normally, we recommend to have this so-called reduced airflow with 0.3 and 0.6. If people are out, you can go down to about 30% of the nominal airflow, and this is 0.1 to 0.3, so that it's not smelling if people come back to the apartment, and it's quite low, but it's a good compromise. Well, but what you can see, the intense flow rate, maybe for a party, or if there are very many people in a classroom or a meeting room, this intense flow rate, this need not be covered in any way by the ventilation system, but this can be covered by window ventilation. So in addition of open windows. And this is what we called before this hybrid ventilation. And from our point of view, it's a quite good compromise to get for. And not at least, the point is, you with that strategy, you can have your ventilation system at a moderate cost level. Yeah, because if you have to have very high airflow with low pressure losses, you would have to have very large ducts, and this is costly. Yeah, we will come to this in some more detail afterwards. Okay, and with that proceeding, we come to the requirements for ventilation system in some general point of view. And in the next slide, you see the a typical ventilation system, ventilation unit. The green part is the heat exchanger, and you see on the right, the green arrow, outdoor air comes in, and from the fan there, and from the left bottom to the right up, it will be heated up and get for preheated supply air. And the yellow arrow, extract air, is coming from bathroom and toilets and the kitchen, and goes from right top to left below, and will be cooled down and will get out the house, and they get out of the system as exhaust air going out. Well, and here you have this heat exchanger, and well, if you go to the next slide, you see, well, sorry. Wait, now we have the, please go a step ahead to have all text. You see here, the minimum requirements, heat recovery rate is 75. The electrical requirement is, please have the electrical power not more than 0.45 watt per cubic meter an hour. And what you can see, many systems nowadays have a much better thing. We will come into later into some more detail what that means and how it is measured. Well, but to have an efficient operation afterwards, you need an efficient ducting system. And as well, for this, we come into some more detail where we will explain what that means in detail. You have to have good ducts and large ducts, not to get low. And well, afterwards, I will show some comments about airflow balance. This is as well a very important thing, and I will show you with the energy balance what does it mean if the balance is not fully arranged well. Okay, next slide is the system on a thermographic picture, and you see the heat exchange means we have warm and cold parts of the system, and this is the picture is just to support the idea that all the system has to be very well thermally insulated, because there are cold parts of the system, and if you put this box inside an apartment, the heat losses will be significant, and therefore you should avoid it. Okay, and with that, again, on the next slide, we have these requirements. First of all, the filters have to be good. here are the filter class F7 for European and the MERV 13 for the American context. So good filters for indoor air coming in, and the extract filters have to be need not be so good quality, but well, we need a filter just to keep the heat exchanger clean. Well, what is very important is there should be not a cross flow between air coming in and air going out. So the air tightness must be good, so that no mixing of air coming in and going out. Well, the next is comfort. Having a good heat recovery, the supply air temperature is minimum about 17 degrees centigrade, even if you have minus 10 degrees outside. And this is a hard requirement because this is about comfort. If you have lower air temperature for indoor air coming in, people will probably complain about draft air and cold air. Well, the next is you should have your system simple, only about 3 levels of operation, as I mentioned before, 70, 100, and 130. Number C is noise. Please care that the system is not noisy. In living spaces, we ask for 25 decibel in A level, and only if it's in bathroom and so maybe a little more noisy. Please do it, otherwise people will afterwards maybe complain about too noisy systems. Okay, next. The efficiency rating I already told you about heat, minimum 75%, and well, and many systems have more. About for electricity, 0.45, I already said, and well, for standby, please have it below 1 watt, as more is consuming energy and doing nothing. Well, good air tightness, thermal insulation I already mentioned, and balance I already mentioned. We come to that later on. Okay, on the next slide, quite shortly, they mention how we calculate the heat recovery rate. You have the formula on the right bottom. It's just the ratio of indoor air and exhaust air with respect to indoor air and outdoor air. Well, the difference indoor air and outdoor air, this is the maximum difference what you could reach. And well, the system cannot have 100% heat recovery, and therefore the difference what the system all it really reaches is the difference between extract air and the exhaust air. Well, and for energy balance calculation, we need the term P electric, because the fan will heat up the air going out a little bit. We have to add it. Well, that's it. Well, Barry will now, well, later explain a little bit more what that means. Well, one thing is this 75 or even more heat recovery, you only will be able to reach with large counterflow heat exchanger. And you see here on the left-hand side, a very large one. In the middle, this is a shorter one. This is the strategy what people go for nowadays. And you see you can do it deeper to reach the same level of heat recovery. What you should never do for passive house and for energy efficient ventilation system is this cross-flow heat exchangers. Well, this might be very small, but it's not suitable. Well, it's too few, and you will have more electricity needed for the fans than you can save energy during wintertime. The another option, as Barry mentioned before, you can go for ERV systems and heat exchanger, and this is on this slide. ERV means you have, together with the heat recovery, the pure dry heat recovery, this heat exchanger can have humidity recovery, as we call it. And that means the membrane, if you use a membrane heat exchanger, the membrane allows for water diffusion from the humid side to the dry side. And that means you can have use of the latent heat of water. And what is more, you can use in wintertime the effect, what Barry explained, the using an ERV or humidity recovery heat exchanger may allow for not so dry air indoor. Okay, on the left hand side, this is a membrane heat exchanger. The same effect can be reached with a rotary wheel, as with that, not only heat will be transported by the lamella, but as well water by adsorption or absorption on the lamella.
I'd like to expand on that a little bit because in the age of COVID-19 and virus spread, this has become a very big subject. And this is a journal, actually European engineering journal, and they shared some guidance for ventilation in buildings. And a couple of big takeaways was with these heat recovery devices, one of the factors that we saw earlier is that the wheels have moisture adhere to one side of the wheel. That wheel then turns 180 degrees and the air going in the other direction. So in the case of exhaust air with moisture in the wintertime, adheres to the wheel turns, and then the incoming dry air picks up that moisture and brings it back into the building. That's how wheels work. And they also transfer heat the same way. The challenge is that viruses on an outgoing airstream adhere to that wheel in the same way that moisture would. That wheel then turns, and those viruses could be picked up by the incoming air and brought back into the building and actually distributed. So their guidance is that wheels should be actually turned off during these periods. And so that's something to keep in mind. Wheels don't have the cross-flow contamination limits that you can get with a counterflow heat exchanger that's well sealed. Another thing that's happening is people are talking about pure ventilation with a dedicated outdoor air system versus a lot of US systems and North American systems use DOAS or don't use DOAS or dedicated outdoor air systems. They use combined heating, cooling, and ventilation systems called RTUs or rooftop units. What you see on the left is a rooftop unit that's got a damper that brings some fresh air in. That's how they provide fresh air to the building. But the heating and cooling is done on a recirculation mode. And recirculating means that you're pulling air from one part of the building and then distributing it back into the entire building or the entire zone serviced by that rooftop unit. As opposed to a dedicated outdoor air system with heat recovery you see on the right, where we're extracting the air directly and all of that stale air goes directly out. We talked earlier about cross-flow contamination limits that Passive House has, and they test those at static pressure differential. In other words, positive pressure on one side and negative pressure on the other, so that you're not seeing any contaminated air pushed across into the supply air stream, and eliminates the possibility of having cross-flow contamination and having viruses spread back into a building. So this is very, very critical. And having the Passive House certified product, those are tested to not have any of that leakage. Another thing is if you are using counterflow heat exchangers with membranes, these membranes are a lot like Gore-Tex, where they allow transfer of water vapor molecules, which are very, very small. And shown here, very tiny water vapor molecules will pass through that membrane, but viruses, VOCs, such as formaldehyde and other pollutants, smells even do not pass through from one airstream to the other. So having a, in effect, certified ERV with the cores made with membranes that are certified, basically, that do not have that do not allow passage of viruses, germs, VOCs, and so forth is critical.
Well, let's here go a little bit into the, with this slide, into the question of energy for the ventilation system. And this comes, with this we come to the requirements of, for the certification of a ventilation system. Here you see an example for of a larger ventilation system, so more than 1,000 cubic meters. We do the testing together with labs, independent labs, which there are some in Europe, but there are as well some in US. Barry may explain it a little bit more. So we, every manufacturer can go with his system to the labs. The measurements are done there, and then we get the data, the raw data, and evaluate the system and care about the quality and the requirements. And if the requirements are fulfilled, you can see it on the next slide. If the requirements are fulfilled, the system gets a certificate from Passive House Institute, and there on the certificate, the useful range for airflow is denoted, the heat recovery rate is denoted, the specific electric power in the under the boundary conditions is denoted, and the performance number, and some other. In the second and third page of the certificate, there is a short description of the system, and last but not least, you have the on every certificate the contact to the manufacturer, so you can directly go there. Well, the idea behind this certification process is we ask for third-party information, so third-party data about the ventilation system, not only manufacturer data, but reliable data, so that the systems are to be compared. Well, and you can go to our website, the passivehouse.com. So many of the systems are available there and with all the data. And on the next slide, you can see there are a variety of systems available, from smaller systems for single apartments, and the larger systems for office buildings and school buildings and so on.
I'd like to address one of the big challenges we've had in North America is that up till recently, there haven't been a lot of, especially commercial HRVs, ERVs, Passive House certified, and we've been relying on a different testing standard in North America. We use HVI, which is a CSA 439 testing standard for small residential up to 300 CFM HRVs and ERVs, and AHRI for larger commercial HRVs and ERVs. And one of the problems is there is a different testing standard. We've mentioned the testing standard earlier. In a nutshell, shown on this slide, you have the red arrow in that house there shows how AHRI and HVI in North America test efficiency. They test the incoming airstream, and they determine what the incoming temperature is from outside and what it's delivered inside versus the leaving air temperature and the percentage of what they call recovered energy. The problem is that incoming airstream has a lot of influences. It's got motors in there that produce waste heat. You've got cross-flow contamination. You've got what they call casing leakage, which Berthold mentioned earlier, where if the box is not well insulated, then you're going to have an influence on that airstream as well. As a result of that number that you get on the efficiency for the incoming air is not a great number for putting into a energy model. Passive House measures, as it's shown there, the blue arrow is the outgoing airstream, and basically they're measuring how much energy is lost from the building. This is very easy. We can determine the temperature of that leaving air, and we can tell you how much energy is embodied in that. It's basically 1.08 BTUs per cubic foot per delta T of Fahrenheit temperature. So if that air is leaving at 10 degrees warmer than it is outside, then it's 10 times 1.08 times the volume. of air. If it's 500 CFM, it's 500 times 10 times 1.08. It's a lot of BTUs. And so one of the most critical things when we're looking at passive house projects, and if you're using the passive house planning package for your energy model, we're showing here the chart there shows 3 different HRVs that were tested to both standards. And what you've got on the left column, the blue column there, it's showing 69, oh, excuse me, that's passive house. The blue is about 70%, 60%, and 93%. The North American method has those at 90, 95, and 94%. So if you plug in 90% into your PHPP and it's actually 70%, you've got a big problem. You're going to have a very different actual energy demand than what you had planned on. So this is really critical. Those 2 standards are completely different. And one of the big takeaways with this slide, these are 6 units that were measured to those 2 standards. And so what you see across the top in those small boxes are the percentage difference between passive house, the blue lower numbers, and HVI, the larger, the red upper numbers there. And you can see the difference is 16%, 17%, 32%, 13%, 15%, 19%. One of the challenges is you can't take a standard correction and just say, okay, I'm going to take my HVI number and just change 12% and just go with that. You have to test because these units behave differently and it's really critical. So that's something that a big takeaway, and we're working to get certifying passive house tested numbers here in North America. We're working with labs, and we have HVI's lab in Canada can now test residential units to passive house, and we're working with the AHRI labs to do the same. To give you an idea, we actually had a project that was shared by Sonia Zouari, a passive house consultant in Canada. This is an actual project that was completed, 42 apartment building. And this shows you the difference between 75%, and they had to use a non-certified, I even doubt that number was actually accurate, and 85%. And when you look at just that 10% difference, what you're looking at on the right is the difference in the demand. It's 40% difference. You're going from 14 down to 10 on your load there, your requirement, and just by that 10% difference in ventilation efficiency. And the penalty between those was 6,600 kilowatt hours a year. When you look at the transmission losses from the exterior walls, and that's a 42 unit apartment building, the total exterior walls transmission losses was about twice what the ventilation penalty was by having 70% instead of 85%. So that's really a critical thing when you're looking at these projects. And Passive House Certified gives you a reliable number that you can use in your model.
So you have now the numbers and the penalty in numbers. Well, if you then have a problem sometimes in your project, you do not have a certified systems available, so no manufacturer can deliver. It's sometimes a question. Well, and as we do not want to stop the projects and we want to go things forward, the question is how to proceed. Yeah, and the idea for that case is, so for the passive house designer or a certifier is, well, if you do not have already certified systems available, you can ask the manufacturer to give manufacturer data. This data, so measurement data from the manufacturer, are sometimes better than nothing if you do not have nothing. So this is the first step to do. But then the idea is just ask the manufacturer to go into the process of certification. And especially for a large system, one idea is the manufacturer can say, well, I'm willing and able to fit for the certification afterwards. So he could go with this system before delivering the system to the construction site. He could go for the lab, maybe going for the testing, and then afterwards going to the construction site. This saves cost, as he does not have to prepare a ventilation system just for measurement. Yeah. Well, and one remark: if you do not have a certified system available, you have to be as a designer and an architect and so on, a building service engineer. You have to be aware that the full responsibility for guarantee is going to you. If you have a certified system available, we can take part of the responsibility, as we can deliver approved data. So please have in your mind and check with the client to go for good quality, and we can help for that from Passive House Institute. Okay, so far for these theoretical things. Now let's go on for some hints in the last part, some hints for quality assurance during planning and realization. So some words about ductwork, balanced operation, and check for everything. First of all, duct systems. Please go for very good ducting, so especially smooth ducting. And what is not allowed is this aluminium ducts, this can be very flexible, and this is a problem. Yeah, the surface on the inside of this duct is very rough, and therefore pressure losses are quite high, and therefore, well, please do not do this. The plastic parts in the middle, these are rough from the outside, but from the inside the surface is smooth, and therefore it's a good compromise. But now Barry will show you some more details about form pieces, what can go wrong. Yeah.
In larger duct systems, more commercial applications, there are different options on components, and I'm just going to very quickly give you a little bit of insight. You want to spend some time looking at this. Just on these, this is elbows and options that you have on providing these, and there may be many of these in a project. Say a multifamily, an office may have many of these elbows. You see on the top the equivalent of 13 feet of ductwork for a radius elbow. A mitered elbow with a square, which you have create a lot of turbulence, is the equivalent of 63 feet of ductwork. And in the bottom, a mitered elbow with turning vanes reduces that to less than 6 feet of ductwork. So when you choose your components, it really has a huge impact on your system. So what this means is you add that all up. If you have 20 of those elbows in your system, multiply 20 times whatever that equivalent is. So if you're multiplying 20 times 63 feet, that's over 1,200 feet of ductwork, as opposed to 120 feet of ductwork if you use the turning vanes. And what this translates into is a very significant difference in the static pressure, and what that means is you're going to use less power to move your fans to move the air through the system. So these pieces and parts really add up, and it's really something to take into account. This is another example very quickly. This is where you have a T connection, and you can see the difference here. The top is just a straight T at 50 feet of equivalent of ductwork. If you put a T with a entry branch into it, they call it, it's 25 feet, so half as much. If you use a Y, it's 13 feet of ductwork. So you're looking, it's about a third as much static. And again, you may have many of those in a system, and then it can all add up. So it really translates into increasing the static in the system, increasing the fan power required, and in some cases, it could be the difference between actually having the unit be able to deliver the amount of air that you promised, which we're going to talk more about. The other thing that's really critical is air sealing. I say here, air sealing is just as important on the inside as it is on the outside. And sealing these ducts is really critical. And it's something that you want to make sure that does get done well, and you can deliver the air to the places you need to in the amount you need. One other thing with ductwork is beware the change order or the out of control contractor. What you can see here, this is the entry point for these two ducts through the roof is over here, excuse me, is here. And we've got all these 90 degrees, that's insulated duct, but the problem is you've got all those 90s that are going to cause a lot of static pressure. The other thing here is that the access is for the filters is right here. You have to actually climb under the duct. So we see this on occasion where the contractor without guidance does these things. This is another project that's got about 30 feet of ductwork on the roof from where the unit is on an old curb over here going to the penetration through the roof here. We were able to fix this. I'd liken this to a Prius. Okay, we've got a passive house certified HRV on the roof, and then we hook a 20,000-pound trailer to it and we expect 50 miles to a gallon. It just isn't going to work. We fixed that, and that's what it looks like now. So we put it on a stand and we put it right where the penetrations are, and this curb and ducting is insulated going directly into the building. We eliminated the problem there.
Yeah. By the way, the effect of this reduction of the length of the pipes, you can check very easily in PHPP. So in PHPP, for every ventilation system, we ask for the length of the cold warm ducts in the cold area and vice versa. And you get very easily the number of the penalty, what you do bad with that. Yeah. Okay, the next, just to show the numbers for what Barry explained with the pressure losses. Each Pascal of extra pressure loss is costly because of electricity, what you need afterwards for your system, and therefore you see on the next slide. Please care for low pressure losses. So take only the range, what you see on the right-hand side, and not too much. And check for a short and large, short ducts and large enough in diameters, and care for pressure losses for each element you have in there. Okay, the next topic is the airflow balance. As I mentioned already, now into some detail, we want to have a balanced airflow, so outdoor air coming in and exhaust air going out should be the same. And on the next slide, you see what about the energy. If you do 100% balance, you have the blue bar on the right-hand side. 100%, it's the blue bar is the remaining what's from heat recovery, so we do not have 100% heat recovery. Therefore, we had some remaining heat losses, as you see on the left axis. And the light blue is the infiltration heat losses. This is typically what you have with a passive house, because we are not 100% airtight. Airtightness is 0.5 in this example at 50 Pascal. Well, but if you go down with balance to 95, 90, 85 or so on, you see the infiltration is going a little bit less, but the disbalance effect is going up. And therefore you see 90% balance, so 10% disbalance is, so to say, allowed. You can have it, but going lower is not a good idea. Yeah. Well, and by the way, you see in this graph, the red line, this would be the energy, the ventilation heat losses if you go without heat recovery. Yeah. Okay, so do it balanced. And if you go a step further, the next slide, you see it may be even worse if you have a bad air tightness. So the lower two graphs is air tightness 1.0 at 50 Pascal, and the left column is heat recovery 75%. Yeah. So we have to have a good heat recovery. We have to have a good air tightness, but in addition, we have to have a well-balanced operation of the system, so to have the good operation of the ventilation system. Well, and on the next slide, you see the airflow balance, how to realize it. And the most simple thing nowadays is to have constant flow air fans. They are able to keep a constant airflow for a longer time. So, by the way, if a filter is in the system for a longer time, the pressure loss will get higher, and this constant airflow fans can compensate this, and so the airflow will be balanced for a longer time automatically. Yeah. So newer systems and larger ventilation systems have it included since a long time. The smaller systems are now getting better and better. But please care on this and ask the manufacturer to get this. Well, and now the last part is about adjustment. Just a few hints about what we need: silencers, filters, and check for installation. So first a remark, please, we do have to install silencers, as otherwise the noise level would be too much in the end. And silencers are a little bit costly, but it's worthwhile to do it. And even if we have air conditioning system, please, the people, your client will be happy about this afterwards, not to hear something from the ventilation system. Next point is air filters. Please provide filters with a low pressure losses, and this means have large surface area available for the air going through. And these bag filters on the pictures are the best example for this. So the longer the bag is, the better. And the idea is you can have these bags in a very small space, and the pressure losses will be quite low for a long time. So have a little more money for these filters here, for the better filters, and you will be get it paid back later because of lower operation cost. Well, and the last point, the adjustment of the system. Here you have the numbers out of the design for each room, the cubic meters. And on the next slide, this is a table which could be provided to the operation people who do the measurement, who did probably the installation, and who do afterward the measurement. They see the numbers, what comes out of the design, and they have to enter in the empty part what are their measurement. And please, next step. The idea is the disbalance should never be, in reality, should never be more than 10%. And so it's good enough. Well, some hints in the next slide. The measurement can be done quite easily. If you use sophisticated system, here the very simple system tools for measurement. For that, you need an experienced engineer to do the measurement. But on the next slide, if you have sophisticated systems, it will be quite easy. Well, the systems are a little bit more costly, but for those companies who do more ventilation systems a year, it might be very well invested money. Well, my summary is just the agenda from before. In the end, on the last slide, care about air quality, air quantity. Be careful not to have too much and too few. Care about the ventilation system. Check for requirements, and we recommend to have it certified. Well, and then last but not least, care for the quality during planning and during realization. Look twice or 3 times and care for people doing this so that everything is working well in the end, and your client will be hopefully happy.
And I'll just say that if you want good ventilation, you need a great ventilator, and that's Passive House certified. Thank
Okay.
you.
Yeah, thank you very much. Bye-bye.